This is the second video for Chapter 7, and in this video we'll discuss the confidence intervals. This is the interval estimate using the central limit theorem from the previous video. That was the point estimate. This is the interval estimate. Now these confidence intervals are tagged with a confidence level. So you want to have so much confidence, like 99% or 95% confidence, that the mean is in this certain interval. Those intervals are determined, and those percentages for the confidence level are determined by the areas under the bell-shaped curve. So if you recall that if within one standard deviation of the mean is 68%, approximately 68% of all the values, or of the area under the bell-shaped curve. If you go plus and minus 2 standard deviations, that area is 95.4% of all the area under the bell-shaped curve, and same with 3 standard deviations is 99.7%. So remember, as you move out from the mean, the percentage of the area that's underneath that curve increases. So now with that in mind, we're going to move to the confidence intervals. So y bar is going to be a sample mean. And let's assume, we have to assume, that the standard deviation of the population is known. However, if it is not known, then the standard deviation of the sample can be used if the sample size is large enough. So here we're going to use a normal distribution and look at z values, because we're assuming either one, we know the standard deviation of the population, or the sample size is large enough that we can use the standard deviation of the sample size instead of the standard deviation of the population. So of course you might say, if you know the standard deviation of the population, why would you not know the mean? Why would you have to come up with some confidence interval? And that is a question. Okay, so basically for the most part, we're going to assume we do not know the standard deviation of the population, but that the sample size is large enough so we can use the standard deviation of the population. But I'll use sigma here anyway, just for, and you can remember you can substitute for it. Okay, so if you remember, if you went out plus or minus 1 standard deviation, that would cover 68% of the area under the bell-shaped curve. Now for confidence intervals, if we go out, okay, plus or minus, this is the population standard deviation divided by the square root of the sample size. If we go out that far on either side of the sample mean, that is going to be our confidence level of 68%, because that will be related to 68% of the area under the bell-shaped curve. Okay, so if I go out to 95.4, that would be 2 of these instead of 1. So let's see how this would work. Here's that sample CDs from the previous lecture. So the mean was 64.4, and here we're using mu, but that's good for the point estimate, but for the interval estimate we'll call that y bar, and the sigma of 2.4 is really the standard deviation of the sample. Okay, let's say that's one sample, forget the histogram part. Okay, for a 68% confidence level, the population mean, the real mean, lies between y bar, okay, and the y bar is 64.4, that's where you see it there, minus or plus the standard deviation over the square root of n. So 64.4 minus 0.48 or plus 0.48, and it gets this other value. So the confidence interval for 68% confidence is 63.92 to 64.88. Okay, and we'll see in a minute. We've assumed there's a 1 here, and the 1 is related to the 68%. Let's repeat the calculation for a 99.7% confidence. Recall that 99% of the area under the curve is 99.7% of the total for Okay, if you're plus or minus 3 standard deviations away from the mean. So here's our mean, and now you see this 3? We use the 3 up here. Okay, got it? Okay, so I repeat the calculation, and now I have the mean for the 99.7% confidence. Okay, you notice this is a larger interval than the previous one. The larger the confidence interval level, larger confidence levels have larger confidence intervals. I mean, I'm 100% certain, for example, that the mean is between 0 and infinity. Okay, so the more confident you want to be, the more vague you have to be. So right now, what we've done here is for some confidence levels of like 68% or 99.7%. Those aren't real handy. Usually people talk about 90% confidence, 95 or 99. These are nice round numbers for confidence levels, but they don't translate into nice round numbers for the number of standard deviations you are away from the mean. So there's another. For example, what we had before was, I'll write it with mu. Oops, sorry. It was mu plus or minus 1 sigma. Okay. Or that was for the 68%. And then we had 1 plus or minus 2 sigma, and then we also looked at 1 plus or minus 3 sigma. Right, 1, 2, 3. Now, if you want to move away from this scheme here, you're going to end up with different values in front. In this case, you end up with 1.65. Right. How do you find that? You find it by looking at, if you want 90% of the area under the curve, that means you want to throw away 10% of the area. And that 10% of the area is divided into 2 tails. So you want to throw away the 5% of the upper tail and 5% out of the lower tail. So you look on the standard normal distributions and you work backwards to find out where that edge would be for that 5%. Here the values were 1, 2, 3. This one is 1.65 for the 90%. This term right here, this multiplier, all the way through here, has a name. It's called Z, and then it has a subscript, alpha over 2. Right. The confidence level is stated in decimal. Alpha is 1 minus the confidence level. In other words, alpha is the amount that you're going to throw away. You divide by 2 because there are 2 tails. So here's an example. We want to have a 90% confidence level, so we want this area in here to be 90% of the total area. That means we're going to throw away 10%. We have to throw away the upper 5% up here in the upper tail, and we have to throw away 5% down here in this lower tail, and that leaves 90% of the area centered about the mean. The question is, what is this value right here? Right. That's the value you have by taking, you can do it in R or you can do it in tables, and you work backwards and you find out what value of Z will give this area of 0.05. Because of symmetry, whatever this is up here will be the same, just with a negative sign, because it's symmetric, about 0 being that this is the Z, these are Z values. So here are the handy values right here. For the 68%, Z alpha over 2 is 1, and that's what we saw before. 95.4, it's 2. 99.7, it's 3. Those are the nice round numbers, but the confidence levels aren't so good. So if you want 90% confidence level, the Z alpha over 2 is 1.65, and that would be multiplying right here. Okay, 95 is 1.96, and then 99% is 2.54. Okay. So this would be the confidence level interval, the mean from the experiment, from the sampling, minus 2.58 times population or sample standard deviation divided by the square root of n. So it's subtracted on one side, added on the other, and that's your confidence. Those are the limits of your confidence interval for a 99% confidence level. So there's a procedure for doing this in R, and I'm going to refer you to the tutorial for R because I discussed it there and I show all the steps. So that would be the confidence interval for normal distribution in the R tutorial.